Picture the sheer physical scale of like a modern industrial manufacturing plant. You're an engineer, you're standing on the floor, and the ambient noise is just, it's an absolute roar.
Oh, yeah, you can barely hear yourself think in those places. The air is incredibly heavy.
Right. And weaving directly above you is this sprawling, just completely complex network of steel piping.
The plant's circulatory system, basically.
Exactly. Carrying this highly pressurized steam to, power massive heat exchangers, drive turbines, feed delicate chemical reactors. But right now, you, the engineer, have a critical problem.
A very expensive problem.
Yeah, the steam rocketing through your main header is carrying far too much thermal energy. Like the temperature is just way too high.
Which is terrifying,
Yeah.
honestly, because if that superheated steam hits the downstream equipment, the thermal stress, the mismatched heat transfer rates, it could easily warp the reactor internals.
Or cause a complete catastrophic equipment failure, right? Bringing a multi-million-dollar production line to a grinding halt.
Totally. Managing that kind of volatility requires absolute razor-sharp precision. We are dealing with immense pressures and temperatures here, where the margin for error is effectively zero.
It's just wild to think about.
It is. In industrial engineering, steam is incredibly useful precisely because it has such a massive energy capacity. But that same capacity makes it remarkably dangerous if the thermodynamic state isn't perfectly controlled at every single stage.
Okay, let's unpack this. Because in this deep dive, we are going through a stack of high-level engineering notes and real-world thermodynamics frameworks.
To walk through a very real factory boiler problem.
Yes, step by step. We are going to explore the mechanics of diagnosing steam states on the fly and, calculate the exact mass balance of cooling water needed to tame dangerously superheated steam.
Which is a daily high-stakes task for plant engineers. They have to maintain safe boiler operations, protect the piping, and basically keep the whole factory running.
Exactly. So before we can introduce any kind of cooling protocol, we have to know the precise thermodynamic state of the steam flowing through that main header.
Right. You can't fix what you haven't measured.
And the trap here is the phase boundary. According to the notes, the boiler is outputting steam at 30 bar of pressure and a temperature of 233.9 degrees Celsius.
Which is a very specific, very problematic number.
Yeah, because at 30 bar, water boils at exactly 233.9 degrees. We are sitting dead on the saturation curve.
What's fascinating here is that managing steam isn't just about making it hot, It's about controlling its exact quality or dryness. And because we're on that curve, pressure and temperature are completely locked together.
Right, they move as one.
Yeah, we have lost a degree of freedom in our system. Because we're in the middle of a phase change, knowing both the pressure and the temperature is entirely redundant.
So those two sensors on the pipe, they tell us the steam is hot.
But they're completely blind to the actual steam quality. They can't tell us the specific ratio of dry vapor to entrained liquid water droplets.
So we're essentially flying blind on the actual enthalpy, the total energy of the system.
Exactly. A subcooled liquid has a quality of 0.0, right? And 100% dry vapor is 1.0. But we don't know if we have 10% vapor or 90% vapor.
We can't calculate the total energy at all. We have to force the system to give up that information somehow.
And the mechanical workaround engineers use to bypass this roadblock is just brilliant. It's called the throttling calorimeter.
The schematics for this thing in the sources are really cool. It shows a sampling tube inserted directly into the main steam line, right?
Yeah, it basically siphons off a tiny fraction of that mystery-saturated steam.
Yeah.
And then it forces it through a very narrow throttle orifice.
Venting into this small, isolated chamber that has its own pressure and temperature gauges. It's like taking a tiny controlled sip of an impossibly hot factory soup.
I love that analogy.
Well, you can't measure the whole vat safely, so you extract a tiny bit, cool it down just enough to taste it, and use that sample to understand the whole batch.
That is exactly what's happening. By forcing the steam through that restriction without allowing any heat to escape to the environment, which is an adiabatic process. By the way, we're essentially inducing an isenthalpic expansion.
Meaning the enthalpy stays the same, but the pressure drops radically.
Radically. In the framework provided, the pressure plummets from 30 bar all the way down to 100 kilopascals absolute.
Wow, that is a massive drop.
It is, and the physics of that pressure drop are what save us. Because the total enthalpy remains constant, dropping the pressure forces the fluid state rightward on a Mollier diagram.
Pushing it out of the saturation dome entirely.
Exactly. It gets pushed straight into the superheated region.
And once it crosses into the superheated region, the Gibbs phase rule works in our favor again, right? Pressure and temperature finally decouple.
Yes, they become independent variables once more. So the calorimeter's internal sensors read the new lower pressure at 100 kilopascals and a new temperature of 125 degrees Celsius.
And with those two independent data points, we can easily pinpoint the specific enthalpy of that superheated sample.
Precisely. And because the entire expansion was isenthalpic, the enthalpy of our superheated sample is mathematically identical to the enthalpy of the saturated steam rushing through the main pipe.
That is such a clever diagnostic maneuver. You use the physics of the throttling process to reveal the hidden energy state of the main line.
And from there, calculating the exact steam quality of the bulk flow is straightforward algebra. But what stands out to you about how engineers have to manipulate these state variables just to get a baseline measurement?
Honestly, it's the reliance on first principles physics. I mean, modern plants are layered with automated systems, right? But sensors drift.
Oh, all the time. Calibration fails.
Yeah, and when the control room data looks weird, you have to know how to perform these physical calculations to troubleshoot it.
Absolutely. It's the only way to prevent an operational shutdown.
Okay, so the calorimeter gives us our baseline. But diagnosing the enthalpy only reveals the scope of our problem. We have to move to the next operational wall.
Right, because we just confirmed the steam is indeed carrying far too much energy for the downstream equipment.
Yeah, the framework moves us to a section of the plant where the header pressure is 6 bar, but the temperature is a blistering 200 degrees Celsius.
So we are dealing with heavily superheated steam now. And look, superheated steam is fantastic for transport. You don't have to worry about condensation and long pipe runs.
And it's essential for driving turbines, right? You want to avoid liquid droplets eroding those spinning blades.
Exactly. But for heat exchange, which is what our downstream chemical reactor requires, superheated steam is actually terrible.
Really? Why is that?
Because the heat transfer coefficient of superheated steam is drastically lower than that of condensing steam.
Oh, I see. So if we feed 200-degree superheated vapor into a heat exchanger designed for saturated steam, the equipment just won't absorb the heat fast enough.
Efficiency plummets. The thermal gradients across the metal become wildly skewed.
And we risk severe thermal fatigue on the reactor walls. So the downstream equipment demands dry, saturated steam at exactly 6 bar.
Right. We have to strip away the excess specific enthalpy from the superheated flow, bring it back down to the saturation line.
And the industry standard method for this attemperation process is deploying a desuperheater.
Yes.
Here's where it gets really interesting. Wait, so to fix steam that is too hot, we literally just spray cooler liquid water directly into it.
Literally, yeah.
How do we not accidentally just flood the system and lose all our steam?
This raises an important question, and it's exactly why the mass and energy balance calculation is a vital high-stakes daily task. The mechanical reality of this injection is incredibly aggressive.
Right. The factory has a dedicated supply of pressurized liquid water sitting at 6 bar and 50 degrees Celsius.
And we aren't just pouring it in like from a bucket. The desuperheater uses specialized nozzles to highly atomize that 50-degree cooling water.
Spraying a fine mist directly into the path of the 200-degree steam.
Exactly. And the margin for error here is razor thin. It is a massive balancing act. If the control valve underinjects the cooling water,
the steam remains superheated, the heat exchanger fails to meet the process load, and we damage the reactor.
Right. But overinjecting is arguably worse.
Because if we pump in too much 50-degree water, the steam won't have enough energy to fully vaporize the droplets.
Yeah, and those liquid droplets get carried along by the high-velocity steam flow. When that non-compressible liquid slams into pipe elbows or valves,
you get water hammer.
Exactly. The kinetic impact can literally tear the piping supports out of the concrete.
Yeah.
Or shatter the internal metallurgy.
Wow. So we have to calculate the absolute perfect mass flow rate of that cooling water.
We need exactly enough subcooled liquid to steal the excess sensible heat from the superheated steam.
And that stolen heat provides the latent heat of vaporization needed to instantly flash the injected water into vapor,
leaving the final combined mixture sitting perfectly on the line as dry, saturated steam.
Okay, so let's structure this calculation. The sources say we have to set up a steady-state control volume around the desuperheater.
Right, assuming steady-state flow, meaning the mass entering the control volume perfectly equals the mass leaving it over any given time.
And we treat the desuperheater as an adiabatic boundary, right? The steel casing is heavily insulated, so we assume zero heat transfer to the ambient factory air.
Yes, and there's no shaft work being done inside this specific section of pipe, no pumps or turbines altering the energy.
So with those assumptions locked in, the mass and energy balance equation dictates that the total enthalpy entering the system must equal the total enthalpy leaving it.
We have two streams flowing in, the superheated steam at 200 degrees and the subcooled liquid water at 50 degrees.
And one single stream flowing out, the dry, saturated steam at 6 bar.
Exactly. So by combining the mass and energy balances, we isolate the target variable, the ratio of the injected water mass to the incoming steam mass.
So the formula is essentially a tug of war.
I like that.
Yeah, the superheated steam is pulling the energy up, the cool water is pulling the energy down, and we are just solving for the exact center point where they balance out.
Mathematically, the mass of the water divided by the mass of the steam equals the enthalpy of the incoming steam minus the mixture's enthalpy.
All divided by the mixture's enthalpy minus the incoming water's enthalpy.
The elegance of that equation is striking. It isolates that perfect physical center of gravity.
But the algebraic letters, the H's for enthalpy, they only take us so far. Where do engineers get the actual numbers?
That requires consulting standard reference data. Typically, the steam tables established by the National Institute of Standards and Technology, the NIST tables.
Okay, and this is where the rule of state variables comes back into play, right?
Exactly. For a pure substance like water, defining its exact state requires two independent intensive properties.
Intensive properties being things that are independent of the system's mass, like pressure, temperature, or specific enthalpy.
Right, so let's trace our three streams through those tables. First, our incoming superheated steam is at 6 bar and 200 degrees Celsius.
And because it's superheated, pressure and temperature are independent. Looking at the superheated data tables, the specific enthalpy value is incredibly high.
Which makes sense. It reflects the massive amount of sensible heat added beyond the boiling point. The tables also show the specific volume at that state is huge. The steam has expanded significantly.
Compare that to our incoming cooling water. It's a subcooled liquid at 6 bar and 50 degrees Celsius.
Again, independent variables. Pulling the specific enthalpy for the subcooled water, the number is relatively tiny.
Yeah, the density is high, the volume is extremely low, and the internal energy is just a fraction of the steam's. So we have our high-end anchor and our low-end anchor.
Now for the target outgoing stream, we need dry saturated steam at 6 bar.
The keyword saturated means pressure and temperature are locked again, right?
Yes, so we switch to the saturated data tables. And the requirement for dry steam provides our second independent variable.
Because dry means the steam quality is exactly 1.0. It is 100% vapor.
Exactly. Using 6 bar and a quality of 1.0, we pull the specific enthalpy for that precise boundary line.
Okay, so with the three specific enthalpy values defined by the NIST tables, the mass balance equation is fully populated.
We calculate the difference between the superheated energy and the target energy, and divide it by the difference between the target energy and the subcooled energy.
And the final calculation result from the sources is, wow.
It's staggering, isn't it?
Yeah. For every 1 kilogram of 200-degree superheated steam rushing through that header, the automated attemperator must inject exactly 37 grams of the 50-degree liquid water.
Just 37 grams of water to completely arrest the superheat of an entire kilogram of high-pressure steam.
So what does this all mean? Physically.
It perfectly illustrates the sheer magnitude of the latent heat of vaporization.
Right, because we aren't just warming up those 37 grams of water, we are forcing a phase change.
The energy required to break the intermolecular bonds of the liquid and violently flash it into vapor is massive.
So that tiny mass of subcooled water acts like a thermodynamic sponge, just absorbing an enormous amount of sensible heat from the steam.
And the precision required by the factory's control systems to do this continuously is phenomenal.
Because those automated valves have to constantly modulate the injection rate based on flow meters, right, to maintain that exact 37-gram ratio.
Even as boiler loads fluctuate and factory demands shift throughout the day, if the steam flow decreases, the water valve must instantly throttle back.
And if it lags by even a few seconds, the ratio skews, water droplets survive, and you get that downstream water hammer we talked about.
Which is why plant engineers constantly monitor the tuning of these control loops, using these exact manual mass balance calculations to verify the digital outputs.
It's amazing. We've traced the entire physical journey here.
That's a lot of thermodynamics to manage.
Yeah. We started with a phase-locked danger zone where standard sensors were useless. We used a throttling calorimeter to force an isenthalpic expansion, revealing the true enthalpy.
Then moving downstream, we confronted the superheated steam problem.
Right. We mapped the mass and energy boundaries of the desuperheater, used the state variables to navigate the steam tables, and calculated the precise 37 grams of atomized liquid needed to safely flash the system back to dry saturation.
It really is the daily translation of thermodynamic theory into heavy industrial practice. But if we connect this to the bigger picture, there is a fundamental conflict driving the design of all this equipment.
You mean the tension between the thermodynamic ideal and physical reality?
Precisely. The sources bring this up at the end. In thermodynamics, minimizing the irreversibility of a process requires decreasing the driving force.
Okay, break that down for me.
Sure. To make our downstream heat exchanger as efficient as possible, we want to minimize the temperature difference between the heating steam and the chemical product being heated. A gentler thermal gradient increases overall system efficiency.
But the mechanics of heat transfer demand a trade-off. If you decrease that temperature difference, the delta T, the only way to transfer the exact same total amount of heat is to massively increase the surface area of the heat exchanger.
Exactly. The strict rules of thermodynamic efficiency demand larger, vastly more expansive equipment.
But the physical and economic constraints of the real world get in the way.
Oh, heavily. The staggering cost of specialty metallurgy, the massive structural supports required, the sheer footprint on the factory floor, it forces a compromise.
Because you can't just build an infinitely large heat exchanger to achieve perfect efficiency.
Right. So engineers are forced to run the steam hotter than is theoretically ideal, increasing the delta T to push the heat through a smaller, more affordable surface area.
Which then requires rigorous attemperation controls like our D-superheater to prevent that hotter steam from destroying the equipment.
Exactly. Every valve, every pipe, every automated spray nozzle is a physical monument to that ongoing battle between the laws of physics and the constraints of economics.
That is an incredible perspective. The next time you walk past an industrial facility or hear the deep mechanical hum of high-pressure piping, think about the invisible thermodynamic balancing act happening inside.
The constant high-stakes modulation of mass and energy.
And the 37 grams of precision keeping the whole massive system from tearing itself apart. Thanks for joining us on this deep dive.